the launch team was ready to go. This is Atlas Mission Control, live from Cape Canaveral, making final preparations for liftoff.
Atlas Systems propulsion, go. Hydraulics, go. Pneumatics, go. LO2, go. Vehicle electrical, go. Light termination system, go. Melon utilization, go. Centaur Systems propulsion.
At Cape Canaveral, some long-cherished assumptions about U.S. space technology could very soon be rewritten. For the first time ever, an American rocket is scheduled to blast into space, powered by a Russian rocket engine.
Go. Vehicle electrical, go. Light control, go. PCLS monitor, go. Light termination system, go. Telemetry, go. RF, go. Complex systems instrumentation.
We thought maybe we misunderstood each other. The performance of the engines were probably 10 to 15% higher than what we had in the United States.
Booms, go. Launcher, go. Water, go. Complex electrical, go. Allen monitor vehicle loads, go.
It wasn't the same technology we were used to. It was a paradigm shift in what we were expecting.
LO2, ready. LH2, ready. Vehicle electrical, ready. Light control, ready. Atlas Systems propulsion, ready. Hydraulics, ready. LO2, ready. Vehicle electrical, ready.
This is Atlas Mission Control at T-minus 5, 4, 3, 2.
Behind the doors of this warehouse in a distant part of Russia lie what for 20 years was a closely guarded secret. A cache of rocket engines designed for the most ambitious space project ever to be undertaken by the Soviet Union. Today regarded as some of the finest in the world, the engines use a unique technology developed by Russia at the height of the space race. A technology so ambitious that Western rocket scientists thought it impossible to master.
The Russians were very secretive at that time, and although they said they were doing something, they did not tell us what they were doing, and in fact it took a great deal of intelligence gathering to really understand what their direction was. The really important things were having good, clear pictures of what they were building.
In the 1960s, the spy satellites of the CIA were keeping regular watch on the Soviets' vast space launch complex, the Baikonur Cosmodrome in Kazakhstan.
In March, April '63, we saw at least some initial what would be called stakes in the grounds for surveyors and stuff like that in the area that was undeveloped on the Baikonur Cosmodrome. The size of the assembly building, the causeway had all the earmarks for a very large launch vehicle indeed. It was like, hello, what's going on here?
The satellite images clearly showed the construction of a new causeway leading up to two huge launch pads side by side. To the CIA analysts back in Washington, the launch pads were the first hard evidence that preparations were underway for the assembly of a huge new rocket. The sheer size of the complex could mean one thing only. The United States was now in a race to the moon.
In the beginning of the 60s, the Russians were far ahead of us. They had better rocket engines, so with that rocket power, they were able to do lots of things that we were simply unable to do. It was a wonderful period for them. First ICBM in August of '57 Sputnik 1 in October of 1957, and then first man in space, first woman in space, first 3 men in space, first extravehicular activity, first spacecraft to hit the moon.
Russia's achievements in space were down to a unique approach to rocket design, pioneered by one central figure. The anonymous chief designer, Sergei Pavlovich Korolyov, head of OKB-1, Experimental Design Bureau No. 1, and Russia's most senior rocket scientist.
He was very much the dominant figure in the Russian space program. There's simply no counterpart, for example, in the U.S. program. He had responsibility not only for the beginning years, the Sputniks, the manned program, communication satellites, spy satellites, planetary spacecraft. There's no American who had that kind of responsibility. You'd have to equate his work with 15 aerospace companies and about 4 or 5 NASA centers. Very, very much the dominant figure.
His identity a state secret. As chief designer, Korolyov was the most powerful figure in the elite core of the Soviet Space Design Bureau, reporting directly to the Kremlin. Korolyov was the key figure behind Russia's unique approach to rocket design, a pragmatic, hardware-based philosophy in which important design questions were only resolved after full test flights.
In a lot of respects, they were well ahead of the game, but the reason they were well ahead of the game is because they had actually put all the hardware together and had applied that technology far better than we had.
The conquest of space a political priority, Russia's breakthroughs had come through a hands-on approach in which rockets had been built, flown, and improved. And if there were explosions on the way, that was something to be learnt from. From his headquarters at OKB-1 in the suburbs of Moscow, Korolyov started work on a manned lunar mission, with that same experimental, hardware-based design philosophy. But the sheer challenge of getting a man on the moon was a problem on an altogether different scale from anything they had previously undertaken. With the United States already enjoying a head start from their declared goal of landing a man on the moon by the end of the 1960s, the odds against Russia winning were beginning to stack up.
Экспедиция на Луну. Одного космонавта.
As Korolyov's deputy, Vasily Mishin had started working on rockets at OKB-1 after World War II. From the Earth's gravity and the Moon's distance, they soon worked out a lunar mission would need a huge new rocket.
In order not just to get to the moon, but to land on the moon and to bring back an expedition consisting of at least one person, for that you need to put 100 tons into the Earth's orbit. And that means you need to have a rocket which has a starting weight in the region of 2,000 tons.
To build a rocket of the size needed, and within the Kremlin's deadline of beating the Americans, was a challenge beyond any the chief designer had previously undertaken. Korolyov quickly realized they would need new, vastly more powerful engines for the huge new rocket. But Korolyov did not see eye to eye with his usual manufacturer on the kind of engines the new rocket would need. He had no choice but to find an alternative supplier.
Korolyov was forced to go to an aircraft designer named Kuznetsov in Samara. This is a fellow who had designed very good aircraft engines, but that was all the experience he had. That was a big risk for Korolyov.
Kuznetsov had built up a formidable reputation as a jet engineer, having designed the engines for the first Soviet long-range strategic bomber. But he had never worked with rocket engines.
Kuznetsov did not have any experience in building liquid propellant engines. But when he looked at their configuration, he saw that liquid propellant engines, rocket engines, did not pose any more problems than aircraft engines, and realized that this challenge could be solved.
Valentin Anisimov had worked under Kuznetsov on jet engine design, but when the chance came in 1962 to apply his skills to rocket engineering, he seized it. From the Kuznetsov Design Bureau in Samara, on the banks of the Volga River, 1,000 kilometers from Moscow, the team began working out what kind of engines the colossal new moon rocket would need. The basic design of rocket engines is simple. Oxygen and fuel are pumped separately at very high pressures into the beating heart of the engine, the combustion chamber, where they are ignited, propelling the rocket forwards. The higher the combustion chamber pressure, the higher the performance of the engine. Those very high pressures are built up by pumps, driven by a gas turbine fired from the preburner, a mini combustion chamber that draws off part of the oxygen and fuel supply. Faced with the deadline of beating the United States, it became obvious to Korolyov there wouldn't be the time to develop the kind of gargantuan engines needed for the new rocket, christened the N1. With Russia lacking the kind of industrial infrastructure of the Americans, there would only be time to make small but highly efficient engines for the N1 rocket, a total of 30 for the rocket's first stage.
In order to lift off, you have to have more thrust than the gravitational force holding you down. And in our case, we decided to go with 5 engines to do that, provide that thrust. And in the case of the Russians, they used 30 engines. So they used engines that were about a sixth the thrust level of our Saturn V engines. You know, it's a matter of engineering choice which way you went.
But the choice to have 30 engines was one that was forced on Korolyov by Russia's lack of resources. With so many engines, the chances of any one failing would massively increase. To overcome those huge odds and achieve the efficiency and performance Korolyov demanded, the engine designers would have to crack a problem that had always been shied away from as too difficult and too dangerous. At that time, all American and Russian rocket engines worked using an open cycle, in which the exhaust products from the pre-burner that drives the pumps are dumped over the side. A simple but wasteful design. But for the high-performance engines Korolyov demanded, that inefficiency was unacceptable. Russia's engine designers would have no choice but to take an untried and highly risky step. They would have to close the cycle and find a way of safely channeling the exhaust products from the pre-burner back into the combustion chamber to be refired. A potentially explosive process, but one that can boost the lifting power of the rocket by 25%.
Closed-cycle engines require a much better understanding of the combustion process and much better control of all of the stages in that combustion process. As a consequence, you can blow up a lot of engines trying to build one that works. And I think that the Russians did blow up quite a lot of engines.
Mastering the new closed-cycle technology with their experimental test-based approach would take time. Time the Russians lacked in their race to beat America to the moon. Not everything went badly. The Bureau's experience with jet engines gave it a lateral and innovative approach to rocket engine development. The Kuznetsov team realized there were strong similarities between the turbopump assemblies in jet engines and rocket motors.
In the construction of both airplane engines and rocket engines, there is a battle to keep the weight down. In our design, the booster pumps are inside the main pumps. This dramatically reduces the external piping, improves reliability, and decreases weight.
The compactness of the engine was both original and highly elegant.
Well, this design was really a radical design for the early 1960s. Whenever you're designing engines, you want to make it as simple as you can with the minimum amount of parts. So the Russians have typically chosen the single shaft type design for the turbo machinery, which really simplifies and adds to its efficiency and performance.
By 1966, with the key technical challenges behind closing the cycle resolved, the highly efficient engine the chief designer had asked for was within sight. But the project was then struck a devastating blow. During routine surgery in January 1966, Korolyov died. The one figure with the authority and vision to galvanize the system behind the goal of beating the Americans had gone. As the N-1 rocket finally started to make its way out to the pad at the Cosmodrome, the odds stacking up against Russia in the race to the moon looked formidable. By 1967, the first N-1 moon rocket had been assembled at the Cosmodrome. Standing 35 stories high and weighing the same as 400 double-decker buses, Russia's answer to America's Saturn V presented an awesome sight.
I have to say that prior to every launch during those years, we felt a certain trepidation. We were still affected by the large number of accidents that we had witnessed with our own eyes, pretty much since 1947.
Vasily Mishin had been appointed to take over as chief designer in the wake of Korolyov's death, in charge of the 24-hour shifts, working to prepare the rocket for launch. Russia lacked the huge facilities needed to ground test all 30 N-1 engines as a whole. The first launch would take place with the rocket and its system of closed-cycle engines still untried. There would be no alternative but to finalize the design in the same way that all other Russian rockets had been perfected, through a series of full test flights.
Because of our limited resources and capacity, We had to do the bulk of the development of the rocket stages during test space flights. We planned 12 unmanned launches, and we only planned manned flights for the 13th and 14th launches.
The first unmanned test of the rocket took place in February 1969.
Well, when the rocket left the launch pad, in those first few moments there was a sort of uplifting feeling. Yes, it's taken off. Yes, it hasn't blown up on the spot. This was already a great victory. And then, what happened next has gone down in history. There was a fire in the rocket, followed by an explosion. And it has to be said that at the time, we felt this was bound to happen. We hadn't finished working on it.
A minute into the flight, the rocket exploded 40 kilometers from the launch site. Metallic debris had caught inside an engine.
Of course I felt bad. Do you think you would feel good if your engine blew up with a thrust of 4,500 tons? You feel very bad.
Controlling a rocket with 30 engines was proving very difficult. But with another 11 unmanned launches still to go before the first manned flight, the engine's control system was improved ahead of the next launch in July 1969.
This is the launch now, you see. It stopped. Now it's going to fall.
Seconds after takeoff, the rocket fell back onto the pad, exploding with the force of a small nuclear bomb.
We hadn't left the dugout 10 kilometers away when it crashed. That's what saved us. If we had come out, we would not have survived.
The rocket had been launched before the ambitious closed-cycle engines had been perfected. While the debris was still being scraped up from the floor of the Kazakh desert, the race to the moon had come to an end. Just 2 weeks after the N1 disaster, the Americans were celebrating victory in the wake of the successful Apollo 11 mission. But the Russians didn't give up there. True to their practice of evolving the design through actual launches, the engine and rocket were steadily being improved. To prevent the intake of debris, filters were fitted to the engines, and the launch pad was rebuilt ready for the next tests in 1971 and 72.
Well, this is the third launch. I've only seen this on film. I didn't actually see it in real life, only the traces. There's the fire.
And their problems didn't end there. The fourth rocket also blew up. The moon race may have been lost, but by the early 1970s, the proven Russian system of refining through test flights was delivering real improvements in the rocket. A new engine, designated the NK-33, was being finalized, in which the gremlins identified from the launch failures had been ironed out. With new filters and protection against vibration, the high-performing closed-cycle engines the designers had dreamed of were finally ready to fly.
Experience showed that Kuznetsov's engines could be made reliable, but for that we needed those very 4 years by which we lagged behind the United States.
But at the very point the NK-33 engines would be able to prove their worth, the program was cancelled. The Politburo's patience with the N1 had finally run out. In 1974, the political imperative behind the moon race had now gone. As a result, the entire N1 program was cancelled on the orders of the Kremlin, and Mishin was sacked as chief designer.
What if I was unhappy? These things happen, of course. But there were a lot of reasons. I can't say that I was fine. Things were bad. But I survived. I'm still here.
At Baikonur today, the desert is slowly reclaiming the colossal works of the N1 project. After the cancellation of the program, the Soviet leadership ordered the complete destruction of all the remaining N1 rockets and their engines. The entire history of the program was suppressed, and the remaining M1 stripped down. At the Cosmodrome, parts of the rocket were even converted into pigsties.
What does a man feel when he was responsible for the creation of a project, for nurturing it, when this system was created and it worked, and suddenly, at the height of your involvement in the creative process, you're told to cut it short, to put a stop to it? There was a disappointment that is difficult to convey now.
The story of the N1 remained a shameful secret until the early 1990s, when, with the fall of the Soviet Union, information started to trickle out. Visiting American rocket scientists, the first to delve into Russia's achievements in space, were starting to get details of an engine for sale. The engine used a kind of technology very different to what the Americans were familiar with.
The description to me was I think there's something there, go find out. So off we go to start developing contacts. You know, who do you talk to? How do you get there? You know, the barriers that we were looking at looked to be almost insurmountable at the time, but we chewed away at it, finally got the right connections and started seeing some of the data.
Information was emerging about an engine with unusually high performance specifications.
When we went to Moscow, the word got around that we were there, and we went, several times. And what happened is people started coming to our hotel, and one of the people that came was a gentleman from a test facility in Salda, up in Siberia, where they had tested the NK-33 engine. And through him, we were able to arrange a meeting with Mr. Kuznetsov himself.
An unprecedented invitation followed to visit the design bureau at its secret location in Samara. There was something they wanted the Aerojet visitors to see.
Literally a forest of engines. There were over 60 engines stored in this one area, just side by side. To see that kind of quantity of this tremendous asset was absolutely incredible.
He was speechless. There's that saying, it took his breath away. He saw them and his jaw dropped. There was a forest of engines. He was amazed.
In defiance of the Kremlin's orders, the stockpile of NK-33 engines left over from the moon effort had been preserved in a warehouse safe from prying eyes for almost 20 years.